Welcome. So today we're going to talk about time series, and this is for Year 10 mathematical method. Time series is a sequence of points in which the consecutive differences in the independent variable is constant. Now remember, the independent variable should be the variable on the horizontal axis, and that is what the other variable depends on, hence it is independent. And the independent variable represents time, hence time series. So when plotted, line segments connect consecutive points of a time series. Let's have a look at example 1.65. We have S, Tn, Sn. So the first coordinate is time, the second coordinate is the second coordinate of the time series. Okay, so notice that we have 1.2, 1.4, 1.6, 1.8. The consecutive difference there is a constant, and it's equal to 0.2. So the consecutive difference in the independent variable is constant in this example. So this is an example of a time series. Now, if we further have Sn plus 1 minus Sn over Tn plus 1 over Tn is constant. And so what that means is, for example, minus 6.4 minus 7.8 divided by 1.4 minus 1.2. In other words, we take consecutive points to form these differences. So if that happens to be constant for all n, then the time series is linear. Okay, now notice if we have a time series that the difference in the consecutive times, that's constant for all n. So to measure whether we have a linear time series, we just need to measure the difference in the consecutive S value. Is that constant for all n? So let's check that out for this example. So here, if this is S1 and this is S2, we have S2 minus S1 is minus 6.4 minus 7.8. And so that's 7.8 minus 6.4. And so for this, we get 1.4. Okay, now let's try the next consecutive difference in the S values. So S3 minus S2 in this example is minus 4.1 minus 6.4. And that gives us 6.4 minus 4.1, which is 2.3. Okay, now notice 2.3 and 1.4, they are not equal. So we have a time series, but it's not linear. Okay. All right, let's have a look at example 1.66. Plot the data in this time series where the dependent variable represents a percentage change in share price over that time interval. Okay, so all we have to do is plot this, or try our best on paper here to plot this. I'll draw some axes with T on the horizontal axis and S on the vertical axis. Now T is the independent variable, S is the dependent variable. And so let's mark out, let's suppose this is 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8. Okay, and then we have, let's suppose, here we have minus 7.8. And so we have a point there. That's our first point in the time series. And then we have minus 6.4. Well, that would be a fair bit higher, say up here. And then we have minus 4.1, that would be a fair bit higher, something like this. And then minus 5.3, that would be a little bit lower, something like this. Okay, now, I don't know if I said so earlier, but this is not the t-axis and this is not the s-axis, because that would make this point here the origin, which is not, so the origin has to be elsewhere. All right, so let's move on to the next page. Two variable data and scatter plots. A bivariate data set is a set of points xn, yn relating the dependent variable y to the independent variable x. So the difference here is that the difference in the consecutive independent variables don't have to be constant, and that doesn't have to represent time. A scatter plot is a plot of points in a bivariate data set where the independent variable is shown on the horizontal axis and the dependent variable is shown on the vertical axis. An outlier is a point of a bivariate data set which is deemed to be isolated from other points of the data set. So, for example, if we have some points like this that may seem to fit a pattern or a line, and then we have another point, say, out here, this would be an outlier because it's away from the pack there. Let's just label that one outlier. A bivariate data set has correlation if the points closely fit a line. Correlations are described as strong correlation or weak correlation depending on how well they fit a line. The data has positive correlation if the slope of the line of best fit is positive. The data has negative correlation if the slope of the line of best fit is negative. Okay, so let's draw a picture. Something like this would be positive correlation, and something the other way, like this, would be negative correlation. Okay, let's move on to example 1.67. Consider the bivariate data set consisting of the points 1, 3, 4, 2, 5, 1, 6, 0, and 9, minus 2. Draw a scatter plot and describe any correlation observed. X and Y. Okay, 1, 2, 3, 4, 5, 6, 7, 8, and 9 out there. And then let's put 1, 2, 3, 4, 5, and 6. Okay, so the point 1, 3 would be here. 4, 2 would be here. 5, 1 here. 6, 0 would be here. And 9 minus 2 would be somewhere like this. Okay, well, the camera fell down. Anyhow, continuing. Let's have a look at guessing a line of best fit. Given a bivariate data set S, we can guess a line of best fit by choosing 2 points x1, y1 and x2, y2, and hence a line connecting them such that half of the points in the data set are above the line and half of the points in the data set are below the line. The points x1, y1, and x2, y2 do not need to be in F. Okay, this is not what we usually do when we find a line of best fit. This is the very, very easy version of it. Recall that the slope of the line passing through 2 points x1, y1 and x2, y2 is given by y equals mx plus c, where m is y2 minus y1 over x2 minus x1, and c is y1 minus mx1, where m is this. Or equivalently, you can calculate that via c equals y2 minus m x2. So these are going to be the same. The construction of points in the data range with a line of best fit within, that should say, construction of points within the data range with a line of best fit is called interpolation. The construction of points outside the data range with a line of best fit is called extrapolation. Example 1.68. Consider the bivariate data set. S is the point 1, 4, 2, 6, 3, 5, 4, 8, 5, 12, and 6, 11. Draw a scatter plot, guessing a line of best fit, and describe any correlation observed. Okay, so let's find our points. 1, 2, 3, 4, 5, 6, 7, 8, 9 on the x-axis. And then we'll put 1, 2, 3, 4, 5, 6, 7, 8 on the y-axis. All right, so the point 1, 4 will be here, 2, 6 roughly here, 3, 5 about there, 4, 8 something like this, and then 5, 12 is way up here, and then 6, 11 will be something like this. Okay, so there's our scatter plot. Now we want to guess a line of best fit and describe any correlation observed in the terms that we've learned. So a line of best fit would have half of the points above the line and half below the line. So something like this. And so the idea here when we do this mathematically is once we fix such a line, we note the endpoints of our line segment, and then we use this formula up here to construct that line of best fit using these. Okay. Now, describe any correlation observed. It looks like we have a strong correlation, and it's a positive correlation. Why is that? Well, we've got a positive slope in this line of best fit. Okay, now with the same data, which is here, and the point 0, 1, and 6, 13, use those to find the equation of the line of best fit. All right, so first we want to construct the slope. M is, remember, y2 minus y1 over x2 minus x1, which is, in this case, 13 minus 1 over 6 minus 0. Okay, so that's 12 over 6, which is 2. So we've got a slope of 2. So next what we do is we say, well, the line is y equals mx, but m is 2, so 2x plus c. All right, but now we don't know C, yet we can find it. So C, remember, is we can just take this to be y2 minus 2x2 using the point x2, y2. Okay, and so that would be 13 minus 2 times 6, which is 13 minus 12, and that would be 1. Now notice if we used x1 and y1, we should get the same thing. So let's do that. So that's 1 minus 2 times 0. Again, that's 1. Okay, so we find that C is 1. So y equals 2x plus 1. So that's a 1.